Good day to all of you, especially to my classmates in Master in Engineering Management. Special mention also to our course facilitator, Dr. Ryan Jan De Lara. By the way, I am Engineer Rani Ann Nemi, your presenter for the topic Inventory Management. This is a topic on the subject Production and Operations Management. So let's start. Inventory Management. So this report discusses inventory control policies for effective materials management in an organization. Whether making things with materials or using them to provide services, materials are the major circulation system of supply chains. Materials are used in making goods and providing services. So materials flow through the supply chains, which must always begin with raw materials. So production and operation management transform the raw materials into materials that are work in process and finally into finished goods. So these are the goals of this report or this presentation. First is explain what inventory management entails or requires. Next is describe the difference between static and dynamic inventory models. Next, discuss demand distribution effects on inventory situations. Number 4, discuss lead time effects on inventory situations. Describe all costs relevant to inventory models. Next is differentiate inventory costs by process types. Explain order point policies or the OPPs and when they are used. Discuss the use of economic order quantity or the EOQ models for determining the optimal order size for batch delivery. 9. Discuss the use of economic production quantity or the EPQ models for determining the optimal production run for continuous delivery. 10. Explain the operation of the perpetual inventory model and explain why it is the most widely used inventory control system. Next is explain the operation of the periodic inventory model and describe the special circumstances that make its use desirable. Next is describe the quantity price discount model and explain how it indicates when a discount should be taken. And last, perform ABC classification of materials. Okay, so what is materials management? So materials management is a system of broad-based planning and control over one of the most important components of the cost of goods sold. It involves organizing and coordinating the materials management system. So what is the materials management system? So this is all management functions that are responsible for every aspect of material movements and transformation. So we have here three main classes of materials that must be purchased and managed. First is raw materials. So generally, these are extracted from the ground and then refined. So second are components and sub-assemblies. So these are composed of raw materials that already have experience value adding. Next is work in process. So this can be stored and eventually shipped as finished goods. Okay, so now let's discuss what is inventory. Inventory is those stocks or items used to support production, supporting activities, and customer service. So in supporting production, these are the raw materials and work in process items. In supporting activities, samples are when you are supporting maintenance, repair, and you support operating supplies. For customer service, these are the finished goods and or sample spare parts. Now, what are the functions of inventories? Why do we need to use inventories? Or why do we need to manage inventories? First is it reduces dependency of one subsystem on the others. Suppose we have this flow of materials. So materials came from the suppliers, then next is to the manufacturing, and eventually to the market. So as you can see, these three subsystems are rigidly connected with each other in such a way that there is no inventory stock in between them. So what do you think will happen? Therefore, the impact of any disruption in any one of the subsystems will be felt in the other two. For example, if production output stops in manufacturing because of some reasons such as power failure, machine breakdown, a strike, etc., then it will not be possible to supply the goods in time to the customer, hence affecting the market subsystem. Similarly, if suppliers fail to supply raw materials and purchase parts in time, then the manufacturing subsystem and in turn the marketing subsystem will be affected. Number two function of inventories is it helps in developing smooth production plans during aggregate production planning process. Next is inventories are built in anticipation of shortages and price increases. And last, it helps in taking advantage of price discounts. Next, we have here types of inventory situations. So first, order repetition, demand distribution, stability of demand distribution, demand continuity, lead time distributions, and dependent or independent demand. So first is order repetition. So it's either static or dynamic situations. In static inventory, models have no repetition, whilst in dynamic inventory, models place orders repetitively over long period of time. So there are two basic models of static inventory models. First is the economic order quantity or the EOQ, and second one is the economic production quantity or the EPQ. So later on, we will discuss more about the economic order quantity and the economic production quantity. But first, for the EOQ, it is a model that is designed for buying items to satisfy replenishment requirements of continuous demand, whilst in EPQ, it is a model that is designed for determining the batch, also called lot, in which an item will be produced. Next is demand distribution. So when discussing demand distribution in the context of certainty, risk, and uncertainty, we're referring to different levels of predictability or variability in customer demand. Understanding the level of certainty, risk, or uncertainty in demand is essential for businesses to implement effective inventory management practices and ensure they meet customer needs while minimizing excess stock. In a situation of certainty, demand is known with complete assurance. This means that businesses have precise information about the quantity and timing of customer services or orders. One example of certainty is signing a contract to supply a given number of units. This converts demand from a risk to a certainty. Generally, there is a cost to certainty because contracts reduce the producer's risk, and then the buyer expects the price will reflect this fact. Now, in a situation of risk, Demand follows a known probability distribution, but there is some level of variability or uncertainty involved. Businesses have probabilistic information about customer orders. Safety stock levels may be used to buffer against variability in demand. As defined, buffer stock is stock carried to prevent outages when demand exceeds expectation. Later on, we will also discuss more about buffer stock. Now, in a situation of uncertainty, there is a lack of historical data or clear probability distribution to reliably predict demand. This makes it challenging to make accurate forecasts. So uncertainty means that there is no good forecast for the probabilities of demand and or the lead time distribution. When uncertainty exists, the probabilities for various levels of demands occurring are speculative. However, when there is a known risk, some planning can be done. When forecasting is difficult because there is no history, systems are developed to search for advance warning, and then efforts are made to gain some control over the uncertain occurrences. Example of uncertainty situation is launching a new product in a market where there is no existing demand history, or maybe in entering a market with rapidly changing trends. Now let's go to stability of demand distribution, which is either fixed or varying. Fixed demand distribution means that demand for a product or service remains relatively constant over time, while varying demand distribution means that the demand for a product or service experience fluctuations and may not follow a consistent pattern. Next is demand continuity. In demand continuity, there is what we call smoothly continuous or sporadic, or in other terms, steady and consistent rate. So here, orders are received at a steady and consistent rate without significant spikes or fluctuations. And then we have lumpy demand, or the periods of high demand followed by periods of low demand. That's why it is called lumpy. Next is lead time distribution. So it's either fixed or varying. As defined, lead time is the interval between order placement and order receipt. Some effects of lead time on inventory situation. Variability of the lead time will be a factor in setting the size of the buffer or the safety stock. And long lead times, sometimes correction of errors takes longer. Kasi kung mas mahaba yung lead time, therefore, mas mahaba din yung time bago mo ma-quality check yung mga items. So if there are errors or mistakes, matagal din siya bago ma-correct. Next is dependent or independent demand. So in independent demand, it is not influenced by the demand for any other item. So consumer goods like electronics, apparels, and food items typically have independent demand. Their demand is directly influenced by customer needs and preferences. Whilst in dependent demand, it is directly related to or independent on the demand for another item. It is usually associated with components or sub-assemblies used in the production of a finished product. So sample are the parts used in manufacturing such as nuts, bolts, and circuit boards. So they have dependent demand. Their demand is linked to the production, schedule, and quantities of the final product. So in OPP or the order point policies, inventories of materials have continuous demand. So later on, we will discuss more about OPP or the order point policies. Now, we will discuss all costs relevant to inventory models. So we have here six main types of inventory related costs. So first we have the costs of ordering. So this includes those cost items that go into making up and placing an order, following up the order and receiving the order. So these are costs that we have spent for paperworks and other communication expenses. Number two is the costs of setups and changeovers. So the cost of setting up the machines to do a production run. This requires cleaning up from the prior job, which is also called taking down. The process known as changeover and the cost can be significant. So sample of these are the labor cost and the cost of equipment downtime and also the any necessary tooling changes. So all costs related to it. Number three is cost of carrying inventory. So items carried in stocks are subject to cost of pilferage or the petty theft. Next is obsolescence or the sometimes the units lose a value over time, like gadgets, deterioration and damage. So these costs represent real losses in the value of inventory. So an added component of carrying cost is both taxes and insurance, especially if the items or the units are very expensive. Cost of discounts. Accepting discounts by buying at least a certain amount of material involves extra costs that may make taking the discount unprofitable. An appropriate inventory cost analysis must be used to determine whether a discount that is offered should be taken. So mamaya may example tayo dito on how to know if a certain offer of discount is profitable or not. The extra cost for taking the discount are compared to the savings obtained from the discount. Extra expenses include additional carrying costs, and part of these carrying costs is incurred for additional storage space. Now we go to out of stock costs. So, for example, when the firm does not have stock to fill an order, there is a penalty to be paid. Perhaps the customer goes elsewhere but will return for the next purchase. Then the penalty is only the value of that order that is lost. But if the customer is irritated by the out of stock situation and finds new supplier, the customer may be lost forever. So the loss of goodwill or the reputation of the company must be translated into a cost that is equivalent to the termination of the revenue generation of that customer. Depending on the system that is used, such as back ordering, substitution, fill or kill, and so on, various costs of being out of stock will occur. Back order or filling the order as soon as the capacity available or the materials arrive. So this include the penalties of alienated customers. So customer might cancel the order or potentially they are dissatisfied, then future business is lost with them. So some mail order companies prefer to fill customers' order with a more expensive substitute instead of creating a back order. Next is cost of running the inventory system. So these costs are often associated with information system costs called IT costs. So running the inventory system or the cost of running inventory system often associated with the expenses tied to the operation and maintenance of the inventory management system. This includes maybe software licenses, the trainings provided for the employees in the organization, and the IT support. So we have here additional inventory policy costs. So there are the costs for delay, costs for production interruptions, and salvage costs, or the cost required for expediting orders. Now, as mentioned earlier, we will now discuss more about the inventory models. First is the EOQ model, or the economic order quantity model. So this is used for determining the optimal order size for batch delivery. It requires determination of the order quantity, which is the amount of material to be purchased each time an order is placed, or we call this as the Q. So here are some of the variables, constants, and terms that are involved. So later on, we will discuss about the formula for the EOQ model, or for the order quantity. But first, we first defined these terms, or the variables and constant that we will be using. So here D is equivalent to the annual demand. S is the order cost, or the cost of ordering. H is the inventory, or the holding or carrying cost per unit per year, and Q as the order quantity, as we have stated earlier. So how can we compute for the number of orders per year? So it's just D over Q, or the annual demand over the order quantity. For the annual ordering cost, it is equal to D over Q multiplied for the S, or the annual demand divided by the order quantity and then multiplied by the order cost, or the cost of ordering. Now, the average inventory throughout the year is equal to Q over 2. So, paano ba nakuha yung Q over 2? Later on, we will explain that. Next is the annual inventory cost. So this is equal to Q over 2, or the average inventory throughout the year, multiplied by H, or the holding inventory, or the inventory holding cost per unit per year. Now, paano ba nakuha yung average inventory throughout the year na formula, which is Q over 2? Uh, just take note na in EOQ, the demand is continuous and it has a constant rate, or the demand has constant rate. So suppose we have here this example and this graph. Here the Q is given as 1,200, or the inventory is 1,200. Since the demand is constant and continuous, then the inventory reaches zero at the 12 month, at the end of the year. So ano ba yung average nito? The average would be 1,200 plus 0 all over 2 equal to 600. And 600 is half of 1,200, di ba? So they conclude that the formula for the average inventory throughout the year is Q over 2. To strengthen this conclusion, meron pa tayong another example. Suppose naman Q is 600. Again, demand is continuous and constant. So from 600 to 0 after 6 months, and then nag-replenish ulit to 600 units. Then after 6 months, 0 na siya ulit yung inventory natin. So if we will average this inventory in whole year, that would be 600 plus 0 plus 600 plus 0 all over 4. So 1,200 over 4 is equal to 300. And 300 is half also of 600, which is the Q in this case. So again, we can conclude that the formula for the average inventory throughout the year is Q over 2. May isa pa tayong example to further strengthen this formula. Now, the inventory level here is 400 or the Q is 400. Then after 4 months, naubos na siya, 0. So mag-replenish ulit tayo, another 400, and then naubos ulit siya, mag-replenish tayo, another 400. So the average here would be 400 plus 0 plus 400 plus 0 plus 400 plus 0 all over 6. And this would be equal to 1,200 all over 6. And that is equal to 200. And 200 is half of 400. So we can also conclude that the average inventory throughout the year is given by Q over 2. Now let's go to the annual total cost. So this is equal to the annual ordering cost plus annual inventory holding cost plus annual item costs. So paano ba yon? First, here we have the annual total cost. So it's given by D over Q times S, or the annual ordering cost, plus Q over 2 times H, or the annual inventory holding cost, plus D times C, or the annual demand times the cost of that item. Next is annual total variable cost. Since the annual demand would be constant kasi given na siya, then ang magiging variable cost na lang natin is yung annual ordering cost and then yung annual inventory holding cost. So ayan, malinaw naman, no? Now let's have an example to elaborate these formulas. Example. Suppose D is equals to 1,200 units, S is equals to $5, H is equals to $1.2, and C is equals to $12. So below we have this table which we assume the order size ranging from 50 to 300. So dito, i-analyze natin alin ba yung best order size. So the table gives the values of annual ordering cost, annual inventory cost, and the annual total variable cost for several values ranging from 50 to 300. So what is the best quantity to buy? Ang sagot po dito is 100. So paano siya naging 100? Ano yung magandang analysis? Bakit siya naging 100? So discuss natin further. Ayan. In EOQ, the optimal quantity or the optimal value of Q minimizes the total cost and is obtained when the annual ordering cost and the annual inventory holding cost are equal. So ayan. In this equation, we have derived to the formula Q is equal to the square root of 2ds all over H. So if we use that formula to the example, then we will get 100. And if we go back to the table given earlier, you can notice that the ordering cost is equal to the inventory cost. So our optimal quantity here would be 100. So next model is the EPQ model. The economic production quantity or the EPQ model, also known as the economic lot size or ELS model, is used in manufacturing situations where inventory increases at a finite rate and depends on the production rate and the usage rate of the item under consideration. In addition to the variables D, S, H, Q, and C defined earlier in the EOQ model, we define two more variables here in the EPQ model. So we have the P, or the production rate per day, or the daily production rate, and the D, demand rate per day, or the daily demand rate. The values of P and D must be in the same time unit. Ayan. So Q in this case is the production quantity rather than order quantity kasi economic production quantity model ito. So to be made in one lot. And S is the cost of setting up the machine to produce that one lot or the setup cost per setup. Ayan, example, suppose P is equals to 50 units per day, D is 10 units per day, and Q is 500 or the production quantity. So the optimal value of Q is called the EPQ. So what is the time to produce the 500 units? 10 days. And we have get the 10 days through dividing the uh, production quantity over the production um, rate per day, or the P. So TP is equals to Q over P, which is equal to 10 days. So in this figure of the inventory level variation, you can notice that the inventory level is increasing at a finite rate of 40 units per day. So paano natin nakuha yung 40 units per day? It is equal to the production rate per day, which is 50 units per day, less the demand rate per day, which is 10 units per day. So at the end of 10 days, ma-reach na natin yung maximum inventory natin because ang production time lang natin is 10 days to produce the 500. And bakit siya naging 400? Kasi meron tayong constant demand rate na 10 units per day. Okay, so at the end of the 10 days, the total number of units in inventory will be 400. Or we can say that it is 10 times 40, or the time to produce the 500 units, which is 10 days, times the 40, which is the inventory level um, rate per day na nakuha natin, di ba? From the production rate per day less the demand rate per day. So I hope na nagigets nyo siya, na-visualize nyo siya from the figure. So the 400 will be our maximum inventory level, as I mentioned earlier. At the end of 10th day, we stop producing the item and then continue to meet the demand from the inventory of 400 units. So, kailan siya mauubos? At the end of 40 days. Kasi di ba 400 na lang yung maximum inventory natin and meron tayong daily demand na 10 units. So, in span of in a span of 40 days, mauubos na yung ating inventory na 400. And then, we again start to produce the production quantity, which is the 500. So, the production cycle does consist of 50 days. Total production cycle is 50 days. And this is how the cycle continues. Now, for the formula of the maximum inventory, or the IMAX, it is equal to the Q less Q over P times D. Or if we analyze, this is the production quantity less the time to produce the production quantity multiplied by the demand rate per day. And if we simplify this, then maximum inventory, or IMAX, is equal to Q times 1 minus D over P. Average inventory is given by IMAX over 2, and annual setup cost is given by D over Q times S. So to compute annual holding cost, it is equal to the average inventory times H, or the holding cost, and is if we substitute the given formula, so average inventory is equal to IMAX over 2 times H. And if we further simplify from the IMAX or the maximum inventory formula we have derived, Then the final formula for the annual holding cost is equals to H times Q over 2 times 1 minus D over P. Now, what is the total variable cost? So total variable cost is equal to the annual setup cost plus the holding cost. And if we substitute the formulas we have derived earlier, then TBC is equal to D over QS, Q times S plus H times Q over 2 times 1 minus D over P. Ayun. So I hope na nai-imagine nyo yung kung paano na-derive yung formula based from the previous derivation also, from the previous formulas given. Now, the optimal production quantity is obtained by equating the annual setup cost with annual holding cost and then solving for Q. So, parang katulad lang ng kanina, we will equate the annual setup cost and the annual holding cost as equal. And then solve for the Q. And if we do that, we will have this formula Q EPQ is equal to square root of 2ds all over H times 1 minus D over P. So, para mas malinaw siya, we have here an example. Now, find the EPQ of the following problem and also identify the storage capacity required. Given annual demand is equals to 50,000 units, the setup cost is $25, the inventory holding cost is equal to $5 per unit per year, and the production rate is equals to 500 units per day, and the number of working days is 250. So again, these are the given. So the demand per day for this question will be 200. That is 50,000 all over the number of days or the number of working days, 250. So substituting the given to the formula for the QAPQ, we will have the optimal production quantity of 912.87. And para ma-compute natin yung maximum inventory, we will just use again the formula given earlier and substitute the Q in the formula. So we will get the maximum inventory as 547.72 units. Now let's proceed to another technique used in inventory management, which is the ABC classification. So this is a powerful systems concept that alerts everyone. So it says that some materials are more important than others. It is prudent to do what is important before doing what is less important. So paano ba natin classify yung mga materials? So here we have the A item. So they are the item that needs in-depth study to improve its performance. Next is the B type items, and they are the items studied in groups and with less attention to detail. And last is the C type, which are the items set to be as simple as possible to administer. Now we have two examples of ABC classification, the material criticality and the annual dollar volume of materials. Now there are various definitions of critical that fits different situations. A possible description of critical parts relates to the probability of total process or product failure when the part fails. Some processes do not fail because of part failure, but instead the production output is reduced by a significant amount. An alternative definition of criticality could apply to the danger involved in using materials. Flammability, explosiveness, and toxicity of fumes are examples. Crucial safety factors of materials management is needed for those. Whichever definition is used for the word criticality, the procedure is to list the first most critical parts and then next systematically rank order parts according to their relative criticality. So the concept of criticality should reflect the cost of failures, including dangers, loss of life, and losses in production output. For the annual dollar volume of materials, dollar volume is the surrogate for potential savings that can be made by improving the inventory management of specific materials. Start with those items that have the highest levels of dollar volume and rank order them from the highest to the lowest levels. Let's proceed to another inventory model, which is the quantity discount model. Quantity discount is a pricing strategy that offers discount to customer based on the quantity of products they purchase. In certain ordering situations, the supplier may give a discount on the price if the item is purchased in large quantities. This scenario is called quantity discount or price discount. However, the price discount on large quantities may not always lead to total lower costs because large quantities will increase the inventory carrying cost. We have here an example. So, given the annual demand D for an item is 240,000 units, the ordering cost per day, or the S, is equals to $30. The inventory carrying cost per unit per year, or the H, is equal to 30% of the cost price of the item. That is, H is equal to 30% of C. The vendor has quoted the following cost prices per unit. So for price 1, it is $2.8 for order quantity less than or equal to 29,999 units. For price 2, it will be $2.77 for order quantity 30,000 and above. So here are the givens. Let's first assess the price 2, which is the lower. So the EOQ for this price is 4,163, which is less than to 30,000. So we calculate the total cost at this quantity, or the TC, at 30,000. Using the TC equation, then the total contract is $677,505. Note that we use the order quantity 30,000 because from the EOQ formula, the Q here does not satisfy the requirement, which is order quantity of 30,000 and above. Now let's assess the price 1, or the higher price. So from the formula of EOQ, we get Q 4,940, which is less than 29,999, which satisfy the requirement for the price 1. That for the order quantity, it should be less than or equal to 29,999. So we will use Q as 4,140. And if we substitute the formula TC, or in total contract, then the total contract for price 1 is equal to $675,477.93. And if we compare price 1 to price 2, it is evident that price 1 has lower total contract, or total contract cost, which is $675,477.93. Therefore, discounts are not always the best option if you consider the costs, such as the example with the holding or storing cost and the order cost. So this example illustrates that the quantity discount is accepted only when it lowers the total cost. Now, in quantity discount model, there are some factors that make a larger purchase attractive, and this include the following. Is there a possibility of a strike? Can the purchase of a large quantity make it difficult for competitors to buy it? 'Di ba? Parang ang talino na. And then, can the purchase of a large quantity promote further price reduction? There are also some factors that make a smaller purchase attractive. This includes, should there be a change in the material being used? Does this item spoil easily? Does it have to be protected against pilferage or petty theft? And does it experience obsolescence like gadgets nowadays, always upgrading? Okay, let's move on to another topic, which is lead times. A lead time is a critical component in inventory management. It affects when you need to place an order to replenish a stock before it runs out. Lead times is the interval that elapses between the recognition that an order should be placed and the delivery of that order. It is also defined as the interval between reordering and receiving that order and readying the units for use. Note that how the diminishing stock level reaches threshold or Lyman, called QRP on both diagrams. So QRP stands for the stock level of the reorder point. That threshold triggers the order for replenishment. We have here 8 lead time consideration that apply to both EOQ or EPQ models. First is the amount of time required to recognize the need to reorder. Second, the interval for doing whatever clerical work is needed to prepare the order. Next is mail, email, EDI, or telephone intervals to communicate with the supplier or suppliers and to place the order or the orders. Next is how long does the supplier's organization take to react to the placement of an order? Is a system in place for communicating with everyone who participates in filling the order? How long does it take to find out if the requested items are in stock? If the items are not in stock, how long will it take for the supplier to set up the process to make them? And how long will it take to produce, pack, and ship? Next is delivery time, includes loading, transit, and unloading transporter. So this period begins with the product leaves the supplier's control and ends when the buyer takes control of the items. Next is processing of delivered items by the receiving department includes quantity and quality checks, as well as determining storage locations and moving items. Next, inspection to be sure items match specifications either by sampling or 100% inspection is generally required. So time may be required to deal with these problems uncovered by the inspection. And last, computers used for updating records are sometimes unavailable until after normal office hours. Ayan. So we have here two reasons lead times are often treated as if they were fixed or single values. Although lead times are usually variable, yeah, they are often treated as they were fixed or single values. Number one, the amount of variability is small and relatively negligible. Number two, it is complex to assume variable demand and the variable lead time simultaneously. The uses of safety buffer stock or safety stock is a just in case rather than just in time tactic. So the much used perpetual inventory system always employs some amount of extra stock as a protection against surges in demand and delays in delivery. The question is, how much extra stocks? Now, let's discuss order point policies. So OPP or order point policies is defined as the stock level at which an order will be placed. In other words, as withdrawal decreases the number of units on hand, a particular stock level is reached. The number of units, called the RP or the reordering point, triggers an order for more stock to be placed with an appropriate supplier. So OPP models specify the number of units to order. So there are types of order point policies. We have the perpetual inventory system and the periodic inventory system. As defined, perpetual inventory system, here order size is fixed and the interval between orders varies. And here it continuously records the inventory withdrawals. While for periodic inventory system, the interval between orders is fixed while the ordered amount varies. So it is used to order certain items together from the same supplier. Some advanced inventory models mix the use of perpetual and periodic systems with the results that costs are further reduced. Now, for the perpetual or the fixed quantity inventory system, it is said that it is perpetual because it is an online system, tracking the stock on hand or the SOH at each transaction of withdrawal or stock entry. So to design the system, it will be useful to answer the following question. Number one, how many buffer stock units should be carried? The answer involves balancing the added carrying costs for extra stock against the costs of running out of stock. As one cost goes up, the other comes down. Next is when should an order be placed for the buffer stock? So again, the buffer stock should be created as soon as it is determined that it is beneficial to have it. It does not have to be replenished when it has been drawn on or to avoid stockouts because the use of buffer stock is expected to average out at zero. In other words, it doesn't need constant replenishing to prevent shortages. The only times that this will not apply will be if the demand system is changing over time or is unstable. So for example, let's say a grocery store decides to keep a buffer stock of canned goods. They initially stock up extra cans to account for potential fluctuations in demand. Over time, they sell this buffer stock, but they don't need to immediately replace every can they sell. This is because the buffer stock is designed to even out over time, unless there are unexpected shifts in customer buying habits. Next is how often should an order be placed for buffer stock? Once and then whenever the buffer stock level needs to be updated is the answer for this. Number four, how many units should be ordered to meet the expected demand? Again, use the same economic order quantity for this question. Number 5, how often and when should the orders be placed for units to meet the demand? Oh, it states that an order is placed whenever the reorder point is reached or the QRP. Number 6, how does this perpetual system work? In perpetual system work, withdrawal quantities are entered in the computer each time one or more units are taken out of the stock. These items are subtracted from the previous stock level balance to determine the new balance quantity for stock on hand. The first step to understand how perpetual system work is by studying this graphic representation. Here, the EOQ model sits on top of the buffer stack, which is the shaded rectangle. Follow the stock on hand line as it forms an irregular sawtooth pattern. So when demand becomes greater, the line moves down faster, and when demand decreases, the line moves down slowly. Meaning, when the demand is greater, the RP or the reorder point, QRP, is reached more quickly, and the interval between orders is variable. Now, how to know the reorder point and its safety buffer stack? So given by the equation, QRP is equals to D of lead time plus SS. The stock level of the reorder point or the QRP is equal to the expected average demand during the lead time period, that is the DLT, plus the safety stock quantity. So the demand during the lead time period or the DLT is equal to D times LT. The expected demand during LT is a function of average demand per day and the magnitude of lead time. Assuming that the demand follows a normal distribution, the value of safety stock can be determined as SS is equal to zeta times sigma lead time. Sigma LT is the standard deviation of demand during lead time, and zeta is a measure of the service level that we want to provide. Z is a measure of the service level that we want to provide. For example, a 95% service level means that there will be no out of stock situation 95% of the time during the lead time. For the 95% service level, the value of C or zeta is equals to 1.65. So how can we use or how to use the Z table? So our Z value is read as a combination of a number in the first column and a number in the top row. So for the given example, let us find how did we get the 1.65. So corresponding to the 95% level, the value of C in the first column is 1.6 and the value of C in the top row is 0.05. Adding these values, then we have 1.65 as our Z. Now let's move to another inventory control system, which is the two-bin perpetual or the fixed quantity inventory control system. The two-bin system is a smart way of continuously monitoring the order point. It is a simple self-operating perpetual inventory system. So two bins here are marked 1 and 2. The optimal order size of Q units has been delivered. So the first bin is filled to the RP level or to the up to the reorder point. So bin 1 now contains units to cover expected demand in the lead time period plus safety stock. The remaining units for the delivery of EOQ is equal to the Q units put into bin 2. So the bottom of bin 2 is labeled as RP, or the reorder point. When bin 2 is emptied, the number of units remaining are all in bin 1, and they are the RP in number. So withdrawals are made from bin 2 first. When bin 2 is depleted, an order is placed for the EOQ, and further units are taken from bin 1. Each time bin 2 is emptied, a new order is placed. It is equivalent to reaching the reorder point. When applicable, much clerical work is eliminated. This two-bin system is well suited to small items such as nuts, bolts, fasteners, etc. Now let's proceed to the second type of order point policies, which is the periodic review or fixed time inventory systems. Periodic inventory systems are based on review or inventory levels that regular fixed review periods. So the optimal interval for periodic review is given by T is equals to square root of 2S all over DH. So paano ba na-derive yung formula na yon? So recall that D is equals to the annual demand, S is the order cost, H is the inventory cost, and Q is the order quantity. Recall also that the optimal quantity or the optimal order quantity is equal to 2DS times H, yung formula na dinerive natin kanina, equating ordering cost equal to holding cost. Therefore, substituting the value of Q to the equation of Q over D, then the simplified formula for TO is this, square root of 2S over DH. Now, based from this figure or the graphical representation of periodic review or the fixed time inventory system, says that to use the periodic model, first find and set the review interval, then set a maximum inventory level, say M. Now, M is equal to the demand during the review period and lead time plus the safety stock. That is, M is equals to D times the TO or the optimal interval for periodic review plus the lead time plus the safety stock. So D is the average demand per unit time. So it could be in day, week, month, etc. Then at each review, stock on hand or SOH is determined and an order is placed for quantity Q, where Q is equals to M minus SOH or the stock on hand. The value of Q will be different each time an order is placed because in the equation for Q, M is fixed and the value of stock on hand depends on the demand during the review period. So this contrasts with the perpetual inventory model where the order was fixed quantity at variable intervals. Now for the safety stocks or safety buffer of the periodic inventory system, this must include protection against unexpectedly great demand in a review period plus one lead time interval. So S is given by zeta times S of the review interval plus the lead time. So S or the standard deviation during review period plus lead time is given by sigma square root of LT plus TO or the optimal review interval. And Z is the standard normal random number and is obtained from statistical table based on the desired service level. So, like for example, yung ating ginawa kanina na uh, values for the Z, ginamit natin yung Z table. So, to use the Z table, just need to find the service level desired and then add the corresponding number in the first column to the number in the top row. Then sigma is the standard deviation of demand within 1 unit time period. It is said that high-cost items and large carrying cost increase the desirability of short review periods, while high ordering cost and or large setup cost calls for long review periods. So just to reiterate, periodic inventory model is in contrast to the perpetual inventory model where the order was fixed quantity at variable intervals. Okay, so this is the end of my presentation. So in summary, this presentation addressed independent demand inventory system. We have tackled OPP models in terms of demand continuity. We have also discussed costs of inventory. This includes costs of ordering, setups, changeovers, carrying inventories, discounts, stock outages, and running the inventory system. We have also explained how total variable cost equations are set up and solved. We have contrasted EOQ models to EPQ models. There is also a discussion here of the lead time structure, uncertainty, and variability. Next, we have detailed the perpetual inventory system with its reorder point and buffer stock calculations. So this report also explains how quantity discount models work and the ABC classification of materials. Thank you, everyone. Have a great day ahead. Bye.